Welcome back to the Deep Dive. Today we're really getting into the weeds of classification in applied data science.
Yeah, it's a core topic. We're using these lecture notes to kind of unpack how machines figure out how to sort information.
Exactly. I mean, think about it deciding if an email is spam or helping with a medical diagnosis. It's all about putting data into the right boxes.
It really is. And the notes lay out some great examples. It could be binary, just two categories, yes or no.
Like the cancer diagnosis example, is it
Mm.
cancer Y1 or not Y0 or spam, yes or no? Simple, conceptually at least.
But it scales up, right? Like identifying handwritten digits, that's what, 10 categories? 0 through 9?
Or even
Here.
pictures of animals. Is it a cat, a dog, a cow? Lots more categories there.
And we see this stuff in the real world all the time now. Remember that COVID cough detection research? MIT News covered it, and there was that Hive app too.
Oh, yeah. Using AI on, like, cell phone recordings of coughs.
Exactly. Analyzing sound features, volume, frequency, that sort of thing to classify if a cough might indicate COVID. It's a perfect example of classification at work.
Super interesting. Okay, so let's maybe use a more concrete example from the notes to ground this. Predicting loan defaults.
Good one. So the task is, will this applicant default, yes or no? We'd look at predictors, things the notes mention like, are they a student?
Right, yes or no.
What's their current account balance? Their income? Those are the X variables.
And the notes mention a data set 10,000 samples, I think,
Mm.
with a default rate of about 3.33%. So not many defaults, relatively speaking.
Correct. And for the machine to process this, we usually encode it. So no might become 0, yes becomes 1.
Mm-hmm.
Simple numerical label.
Makes sense.
So the big picture goal here, the fundamental aim, is to build this function, this classifier. Let's call it HatYGX.
Right. It takes the input features.
And it outputs a predicted category from the possible set, like default, no default, or 0, 1, 1 beat mark.
And the key is we want it to be accurate, right? To minimize the chance of making a mistake on new data it hasn't seen before.
Precisely, which is different from regression, remember, where we were predicting a continuous number, like a price, and worried about mean squared error. Here, it's about getting the category right.
Okay, so the machine learns patterns from the past to make these categorical predictions.
Got it. Now, as we start thinking about wrapping this up, the notes mention different types of classifiers.
Yeah, there are a few main flavors. You've got linear classifiers. They basically draw a straight line or a flat plane in higher dimensions to separate the classes. I think that is TXer, compared to some threshold.
Okay, simple division.
Then you have nonlinear ones
Hmm.
for when the boundary isn't just a straight line. It might be curved or more complex, comparing some nonlinear function exl to a threshold.
Right, and sometimes you can kind of cheat, can't you? Make a nonlinear problem linear. Sort of. Through feature engineering. Like if you have $1 and $2, you could add a new feature like $i times x to be two others. Suddenly, a linear boundary in this new feature space might do the job.
Clever. And there were feature-based linear classifiers too, comparing theta t to theta threshold.
Essentially applying that linear idea after transforming the features with some function to phi.
Okay. Now, when these things make mistakes, especially in binary cases like the loan default, there are different kinds of errors,
Absolute critical point. You can have false positives predicting a default when there isn't one.
which could mean denying a loan unnecessarily,
Exactly. And false negatives predicting no default when the person will default.
which is bad for the lender.
Right. We often use what's called a confusion matrix to track these true labels versus predicted labels. The notes mentioned for one method, LDA, the overall error rate on the default data was around 2.75%. Not too bad.
Okay, LDA. That brings us to the model-based approaches mentioned using Bayes' rule. Sounds a bit more theoretical.
It is. A bit. The core idea is calculating the probability that a data point belongs to class K given its features X. So P, Y, K, X, IC. Bayes' rule gives us a way to calculate that using the prior probability of the class, the likelihood of observing the data given the class, and the overall probability of the data. So you're updating beliefs based on the data.
Pretty much. This leads to methods like linear discriminant analysis LDA, which assumes the data for each class follows a Gaussian distribution, and crucially, that the covariance matrix is the same for all classes.
And that leads to linear decision boundaries, hence the name.
Correct. Then there's quadratic discriminant analysis, QDA. It also assumes Gaussians, but it allows each class to have its own covariance matrix.
Which means the boundaries can be quadratic or curved. More flexible, I guess.
Potentially, yes, if the assumption of equal covariance is wrong, but it also needs more data to estimate reliably.
Makes sense. Okay, what about logistic regression? That sounds familiar from regression context. It does bridge the gap. For binary classification, logistic regression directly models the probability of y being 1 given x. It uses that sigmoid function, frac1 plus xx1.
Ah, the S-shaped curve.
That's the one. It squishes the output between 0 and 1, making it interpretable as a probability. We typically train it using maximum likelihood estimation.
And it did pretty well on the default example.
Very well. The notes said about 2.73% error, even slightly better with regularization, down to 2.66%. And it extends nicely to multi-class problems, too.
Interesting. Okay, one last approach mentioned. Nearest neighbors, KNN. That sounds totally different.
It really is. It's non-parametric, meaning it doesn't assume a specific model form like LDA or logistic regression.
So how does it work?
Simple idea, really. To classify a new data point, you look at its k closest neighbors in the training data.
Based on distance, I assume.
Yes, usually Euclidean distance. Then the new point is assigned the class that is most common among those k neighbors, majority vote.
Ah, okay. And K is just how many neighbors you look at.
Yep. The notes showed results for the default data. 5NN had a 3.22% error, but 14NN got down to 2.75%. Finding the right k is part of tuning the method.
And scaling matters here, right? Because of the distance calculation.
Hugely important. If one feature has a much larger range than others, it will dominate the distance calculation unless you scale them first, like standardizing them.
Fascinating range of techniques, from drawing lines to asking the neighbors.
It really is. And these fundamental concepts, LDA, logistic regression, KNN, they're the bedrock for so many complex AI systems you interact with constantly.
True. It makes you think about how these building blocks are used and maybe combined or adapted in things like, I don't know, advanced image recognition or the way your phone understands what you say.
Absolutely. And maybe for you, the listener, a next step could be exploring some related algorithms we didn't cover, like support vector machines or decision trees, or even diving into neural networks to see how they tackle classification. It's a huge and evolving field.